Hello everyone, my name is Artyom and this is the next episode of Ray Tracing in Rust. So my plan for this video was to implement 3D vectors, operators on them, and then define a basic 3D scene. And I thought it's going to be like super straightforward, very quick video, 15 minutes in and out, because Rust supports operator overloading via traits like add, div, sub, mul. And I did not at first anticipate complications, but complications arose, and so this turned out to be an hour-long video instead, or something along the lines. So just to give you an idea, this video has kind of three main parts. So part one is me complaining about operator overloading in Rust. And this extra ceremony that comes from having to distinguish between own type and kind of ref types. Then part two is kind of this comparison between the implementation in Rust and the one in OCaml and the one in Scala, just to give you a better idea what things may look like in other languages. And finally, part three is this basic 3D scene setup, given that we have all this, boilerplate with vectors and operators done. And this is kind of, I would say, more or less very straightforward translation from the C++ version from the book to the Rust version in the editor. I wouldn't say it's like it has to do a lot with ray tracing just yet, but it is the required groundwork before we can start rendering something a little bit more interesting. So just a quick recap. Last time we have created this small program in Rust that created an image in ppm format that looks something like this. Actually, it looks exactly like this. And so what it does, it creates an image 256 by 256. So we have defined what an image is, just a matrix of pixels. We defined what a pixel is, and defined what the ppm is, and how to format pixels and images in ppm, and so on and so forth. And we also use some snapshot testing using K9 library. So this is the previous video. Now in this video, what I'm going to focus on is this vec3 class, which is a three-dimensional vector as it's defined here. So we'll define this type and we will overload arithmetic operations on it. So like addition, subtraction, multiplication, division. That's something that we're going to overload for our vec3 type. And then we'll proceed kind of with the rest of this chapter 3, where we, chapter 4, where we define what the array is. I mean, we're writing array tracer, so array, pretty fundamental type. And then we will look into defining this sort of 3D scene where we'll have a camera and a viewport and a bunch of pixels, and we'll be sending kind of rays into these pixels, and in the end we'll produce an image that looks like something like this. So a blue to white gradient depending on ray y coordinate. So that's the plan. So yeah, let's dive right into it. So here vec3 has 3 doubles to hold coordinates. I'm gonna do it a little bit different. So I'm gonna define a struct with just 3 fields. All right, so far so good. Then we'll also need to define some helpers here, something like function new, and this is going to be a little bit boilerplatey, but this is something that we just need to just bear with me, basically. And this is actually something that I really like about Rust. And it's basically about the concision of the code and some of these kind of developer experience decisions. Like in this case, instead of doing something like this to assign field X to variable X, we just use a shorthand. Very nice. Same goes for the use of self. It's like inside vec3 we know what self is. So if we decide to rename this into like a vec3 into something like vec3d or whatever, we don't need to rename a whole bunch of identifiers here. Also, very nice, kind of good focus on developer experience. But let's kind of move forward. So we have this vector, we have the function new that creates a new vector. And so what I would like to do next is probably, maybe start with some of the APIs. Since we're going to be overriding these operators, let's have like a feel for what the code will look like. So I'm going to create another module here, and it's going to be vectest. And okay, whatever. So let's see. We would like to create, a vector. Let's say something like this. 2, 3, 4. Why not? And for some reason it doesn't work. Oh, of course. All right. We can create another one. So far, so good. And then we should be able to do something like this. Okay. And we would expect, let me see, so we use K9 snapshot. Let's do the same thing here. And of course it doesn't compile because basically we have not defined this addition operator for vec3. So let's do this. Kind of the most straightforward thing that actually comes to mind is to just define impl add for vec3. Okay. And okay. So the result of the addition is going to be vec3. And this is actually, again, like another design decision, nice design decision about the add trait is that, you have basically the, the left-hand side, vec3. Then you have, if you take a look, the add is actually parameterized by the right-hand side, which is by default the same type for which we implement the addition operator. And then there is the output type, which in this case is vec3, but it can be something different, and we'll actually have kind of one example where the output is different from the left-hand side here. But in the meantime, let's do the obvious thing here, which is going to be, so we're going to do vec3 new, and here it's going to be like self x rhs x. All right, so far so good. And if we take a look at this thing, yeah, so we see that we don't have a debug implemented for vec3. And I'm not going to derive debug for vec3 because it's going to be pretty verbose. Instead, what I'm going to do, I'm going to impl debug for vec3. Just, a regular vector formatting. All right, so I think this is good now. Let's run the test. And I'm gonna stop this thing, and instead I'm gonna do cargo test. And exactly as expected, the snapshot doesn't match. So let's do K9 update snapshot, and then we're just going to use cargo watch. And this looks kind of like what we need here. 3.5.46. How about this? Okay, I think this is pretty good. So, so far it looks good. However, let's try to do something. Let's see if we want to reuse v1 in this case. Let's say I want to do v11, which is going to be v11 plus v11. This is actually not going to work. Like this. Still not going to work because here the compiler complains that we use a moved value v1. And I mean, this is actually exactly what is happening here. So if we take a look at the definition of addition for vec3, it accepts, the left-hand side by value, right? So it consumes whatever you pass to it, right? And the same goes for the right-hand side. So this is fine in some cases, but like in other cases, this is not super ergonomic, because if you want to reuse v1 or v2, then you're going to do something like this. And okay, of course we need to derive clone. Not here. Over here. Then it's going to work. Like another option is to make the type not just clone but also copy. Then it's also gonna be fine. Where's the test? Yeah, here we go. But this means that whenever we have something like this, we are gonna copy the whole vector with 3 floats, and this is not necessarily something that we want to do. So let's get back and remove copy from here. And so one way to kind of resolve this is to define another impl for addition, which would look something like this. So let's say we have impl add for vec3, which means that we will just take the vector by reference. Let's do the quick fix, and the output is going to be vec3. So we are going to create a new vec, which is fine. Yeah, well, okay. Now if we go back here and instead do something like this, then it's all gonna work. And this is actually an interesting distinction. So here we have defined a thing like add for a vec3 ref, right? And usually when we define a method, let's say if we go back to the vec3 class and we define a method called add, which will take self by reference, and then it's going to take another, like right hand side, by reference as well. And we're going to do the same thing here. Lots of boilerplate for now, but bear with me. Okay. So we have this function defined on vec. If we go back to this example, we can just do v1 add v2. And come on. Let's rename this as standalone add. Okay. And here we'll just use standalone add. So here, despite that v1 is vec3 own type, we call standalone vec, which takes a ref type. It kind of auto converts the receiver to the ref type, but it doesn't happen the same way with the operators. So if you do v1 plus v2, it is not gonna auto convert. It will just pick the impl for vec3 and therefore require kind of the same vec3 on the right hand side. This was kind of long-winded explanation of how operators are different from regular methods. But the point is, this is actually a kind of long-standing, let's call it an issue. And let me just open it here. Or maybe actually this one's gonna be easier to look at. Right, so autoref, autoderef in operators, which kind of explains this problem. And it actually has this pointer to this impl add for u64, where you have like a lot of different impls. And actually, if you just remind me later, if you just look at, let's say u64, and then we scroll to, okay, let's say multiplication. So we have multiplication defined for u64 with the kind of u64ref with u64ref on the right hand side, u64 with u64ref on the right hand side, and basically like all different types of combinations, u64, u64, like with and without ampersands. Anyhow, so there's a good reason why this was not solved in some way or another, but for us this means that it's we'll just need to live with a bit of a boilerplate for this operator overloading. And now I will probably just shut up and write a bunch of code for different kinds of combinations of vec3 and vec3 ref. And when I'm done, hopefully we'll have a more kind of fluent interface for addition. All right, so basically what we have here, I have defined kind of this basic implementation which accepts both left-hand side and right-hand side by reference. And then I define a bunch of, as again, like I said, different combinations of ref and unref types that kind of just, delegates to the basic version that is defined here. And this means that we can do something like this, right? So we want to reuse these vectors later on. So, we just take references. That's fine. But in some cases, let's say I have v1, which I want to reuse later on, but then I have kind of this constant vector that I, don't need to store in a variable or something. And then I'm just going to do like, 1, 2, 3. Okay. And this is going to use oh, come on. And this is going to use, the overload, which has right-hand side as a reference and left-hand side as a known type. And this is still going to work. And then we can do kind of the same thing with both types to be owned. For instance, all right, and so this, this still works. Which is again a little bit annoying, maybe slightly more annoying than what we have here, but it is what it is. However, we need not just the addition but also subtraction, and then we need to do kind of the same thing again, but for sub instead of add. That's gonna be a lot of code. Well, not a lot of code, but a lot of kind of boring code. All right, let's do the same thing with subtraction. All right, this looks reasonable. Then we need multiplication and division. And we need to define this for basically, I would say, different kinds of numeric types, like integers and floating point. So, and this is actually kind of going to be this example where we will have left-hand side and right-hand side to be, different, not just in terms of the, references, but actually to be different types. So in order to do something like the following, and here I'd probably just, split editor, right. Okay, cool. Let's create another test here where what we want to do is kind of take a constant, let's say 42, and multiply by maybe just 2, and multiply by v1. So far we cannot do this, and so we need to, so if you look at the error here, it says that we need trait mul vec3 blah blah blah. So let's do this here. And so here we'll do kind of the same thing. First, we'll define let's say floating point. The output is going to be vec3. So here we have f64 on the left-hand side. On the right-hand side, we have vec3 ref, and the output is going to be vec3. All right. So this will make the following code work. This needs to be test 3. Yeah. But if you want to do something like this, we still need one more implementation. Ta-da! Right, so this is gonna work, and this is gonna work as well. But then how about something like, so we do the same, but with integers instead of floating point numbers. Oops. All right, need more operators. So the same thing for, so what do we choose? What do we choose? You know what, maybe we just punt on additional kind of multiplication operators for integers, because there are many options. Like we can go with signed, we can go with unsigned. That's just a little bit becomes a little bit unwieldy. So instead, let's define division. So this is going to be something like test 4, and instead of this, we'll be doing divide by 2. Okay. And here we again need to change left-hand side and right-hand side. So this is gonna be f64 for vec3. All right, so this seems to have worked. So now we have addition, subtraction, multiplication, and division. Although when we need to use integer constants, we would need to convert them to floating point first. But that's fine. Anyhow, I think this is fine. And we have a couple more things defined here, like the length and length squared. So let's maybe just, implement these extra functions. And also there is a couple of aliases, like 0.3, for instance. So let's finish this up and then proceed to the chapter 4. All right, so we have a couple more things here, which is a dot product and a cross product of two vectors. And I see that there is an overload of multiplication for two vectors that does dot product. I think this is a little bit confusing. So maybe for dot and cross products, we just define them as regular methods and not as, operator overloads. And so with the color here, what I'm going to do is basically define a function that will take the color, and we can think of the color as a kind of real valued color with components ranging from 0 to 1. And then this function will take the color and transform it into a pixel with values from 0 to 255. And that's going to look something like this. All right. And now we can refactor this thing. All right, this looks good. Let's do cargo run and okay, the image still looks good. Now, before we proceed implementing a ray tracer in Rust, I just wanted to take a moment to kind of compare and contrast what kind of custom operators look like in other languages. Starting with OCaml, because there is another series going in parallel with this one called Ray Tracer in OCaml. Check it out if you're interested. But getting to the implementation in OCaml, this is what vector look like in OCaml. Okay, so we have the vec3d module, and then the vector is just 3 floats, and then plus, minus, multiply, divide. All these operators are implemented in a pretty straightforward way, and we have really not that much ceremony here, in the sense that we have just one definition of plus instead of 4 as we had to do in Rust. So far it actually looks pretty reasonable. However, if we open main.ml, the actual use of vec3d like all these different operators, is actually prefixed with this vec3d dot parent, which is an OCaml's way to locally open whatever is inside this module and bring it into scope. And the scope is basically things inside the parentheses. And to give you a better feel for what it is for, let me fire up the REPL, and then I'm gonna open the race module here. And let me create a couple of vectors. So let's say v1, v2. Now, if I try to do something like this, this is not gonna work because operator plus works on integers. So 1 plus 2 works. To add vectors, I need to do this thing that I explained before, which is actually not that bad, right? But let's say if you have a lot of vector operators, like lots of stuff that needs prefixing with vec3d, you may be inclined to do something like this. Just open the vector, bring everything into scope, and then, you can do v1 plus v2, and it all works just fine. However, if we try to do 1 plus 2, then it no longer works, because plus is a function that expects something of type t, but we passed an integer, and this doesn't work. And if we show t here, this is this 3 floats that come from the vector module. So it is not so much operator overloading, that is happening here, rather, creative use of name shadowing. Okay, it's not as bad as it sounds. At least so far, it actually wasn't that annoying. But I guess like a different perspective might be also helpful here. And for this perspective, let's look at the Scala implementation. So what I'm going to do is open vec3 Scala here. And the implementation of vec3 is actually, I would say it's even more straightforward than the OCaml's version or the Rust version. So we have vec3, that has 3 doubles inside. Operator plus is implemented in a, again, like very straightforward way, single implementation. Not many surprises here. Same goes for minus. Then the division by a scalar value is also very straightforward. And also multiplication by a scalar value, where the scalar is on the left-hand side, is implemented as an extension of the double, right? So basically, we want to do something like okay. And just to have a better feel for how this actually performs, let me open again a REPL here. I'm gonna load vec3 Scala, and let's create the vector. So the same 1, 2, 3, and then v2. Of course, there is no ceremony here. v1 plus v2 works as expected. We don't have to think about whether it's passed by reference or whether it's owned. And also, if you want to do something like 1 plus 2, it still works. There is no need to think about namespaces and whatnot. And something like this also works, and of course this will work as well. So I would say out of all these implementations, the Scala one is actually the most straightforward, the most ergonomic, like really minimum amount of ceremony. And I guess like Scala got a bit of a bad rap at some point because of the, let's say, abuse of advanced functional and type system features. But if you, stick to simpler Scala, then it actually can be like a very pleasant experience where you can get stuff done with very little ceremony. But enough with that. Let's get back to Rust. Now that we're done with the operator overloading boilerplate, it's time to proceed to chapter 4, where we define, rays of ray tracer, and also define this basic 3D scene with the camera and the viewport. Let's start with rays first. So here, the C++ version has ray, which has an origin and a direction, and then we have a function at that scales basically this ray. So let's implement this in Rust. That should be, again, pretty straightforward. So what we're gonna do is, so we have struct ray, we have origin, which is a 0.3, and then we have direction. All right, and if you notice here again, we use our custom operator for multiplication of vectors. So far so good. Now that we have rays, let's see what we have to do further. So we have to work a bit on the scene setup, where basically we want to produce an image with the width of 400 pixels and an aspect ratio of 16:9. So we calculate the image width, image height, and then we will calculate viewport width and height based on this aspect ratio. And so the viewport width height and image width height are not kind of the same. For viewport height, we'll just use constant 2.0, but that's fine because things will just scale in the right way. So another thing here is that the camera is centered kind of at 0, 0, 0, and then so we have, I think, X is going from left to right, Y is going from down up, and then Z axis is pointing in the viewer direction. So it's pointing here, and here it's going in these kind of into the negative, basically. So what we will need to do as well is, so if you look at this viewport, we're going to have like a bunch of pixels inside this viewport. And we need to calculate coordinates of these pixels. And if you notice, the pixel here is not at the border, but it's actually kind of inside this square. So we'll have to do a little bit of kind of vector arithmetic to get this right. But all the code in C++ is actually here. So translating it to Rust, given that we have all the operator, all operators defined, should be, I would say, overall straightforward. So let's do this. I will comment the tricky part if there are any. So here we have this kind of sample image thingy, and what I want to do is I will define another function which will be called basic scene. So we need to do a little bit of like a number conversions from integers to float and back, because Rust doesn't do it automatically for good reasons. So this is a little bit more verbose than what we have here, but still, not very bad. So now let's do the camera part. So now we need to calculate kind of the viewport vectors, which are these vectors along the this axis and this axis. So the author uses VU and VV. I just cannot remember what U and V stand for, so I'm going to use something a little bit more mnemonic. So let's say viewport left right is going to be vec3, and so here we're going to do like the x coordinate is going to be viewport width, and then it's going to be 0, 0, right? Now for the vertical, we're going to do up, down, which is going to be 0 minus viewport height, and then 0 again. Now that we have kind of these vectors that go the full length of the viewport, we need to calculate this delta vector that will be correspond to the distance between pixels. So and this is and here we need to pass this by reference because we're gonna use it later on. Okay. So now we will need this particular coordinate, like kind of the upper left corner of the viewport. And if we scroll here, what we need to do, we need to go, from the camera into the viewport along the Z coordinate. And then we need to go kind of, up and to the left. So this is what we will do in the code as well. So the viewport will be camera center. Then we need to go in this direction by the focal length, and focal length is this distance. So we need to subtract vec3. Then we need to go, half of the viewport width. So we go viewport left, right, divide by 2. And then we need to do the same for up, down. Okay. And finally, we need to calculate the location of this pixel. So this is going to be pixel 0, 0. And let me just scroll down to here. Yep. So this is going to be viewport upper left plus 0.5. And here we have, half of these deltas. Pixel delta left right plus pixel delta up down. Okay. And the rest, I think, should be pretty straightforward. We just do the same thing with the image rendering. So we create new with init. We do image height, image width, and then here we're going to have a function that takes a row and a column. And now that we know the location of 0, 0 pixel, the actual pixel corresponding to row and column will be calculated as pixel 0, 0 location plus row multiplied by, and here we need to cast again, pixel delta up down, and the same thing okay. So we have the pixel center. Now we need to calculate the direction of the ray, and again, very straightforward. We just take pixel center, so ray dir, we just do pixel center minus camera center. Okay, and then the ray will be ray from camera center to ray dir. Then the color will be, this function ray color, which we haven't defined yet, but will. And let's do it here. So this is going to be ray and for now, let's just return just 0, 0, 0, which is black color. And so here we're going to do color to pixel. That's not true. Okay, this is weird. Let me start cargo in the swatch mode. Okay, so this is fine. Okay, yeah, so we need to change this kind of sample image to basic scene. Perfect. Now we have this black square, 400 by 225. All right, so now let's implement the ray color. And so what is happening here, we basically take this direction of the ray, we create a unit vector out of it, which is a vector of length 1. And then we gonna do this blending of two different colors here. So this is white, and this is, I presume, blue. And then we blend it based on the direction of the kind of y coordinate of the ray. So let's see, we have ray. I guess like one helper that we need here is the unit function. So let's do so what we're gonna do is self clone divide by self. Oh, that's not here. And look at this. We have the gradient, and I think it looks really close to this one. Yep. So now I think this one we can just remove. All right, so I think this actually doesn't look too bad. So we do need to kind of convert between integer types, numeric types from time to time. We also need to take, an occasional reference from our vectors because of reasons. But otherwise, I would say this looks very close to this. And yeah, I guess next time we'll actually start doing a bit of ray tracing, because that was kind of not too interesting. That was more like a groundwork just to get up and running. But starting from chapter 5, we will finally start rendering things, starting with the sphere, and then adding a little bit of shading, and then doing some more stuff, adding more objects. Okay. Yeah, so I would say closer to chapter 7, 8, things will get much more interesting. 9 as well, some diffuse materials. All right, yeah. Anyhow, that's enough for now with coding. Wow, that was a lot of ampersands. But at least we're done for today. And I guess like the takeaway is that operator overloading in Rust with traits is a little bit more involved than I hoped it would be. It does require a lot more ceremony than in some other languages. So I'm not sure if it's like a good thing or a bad thing. It definitely feels a little bit off, given that the rest of the language focuses a lot on the ergonomics, and this thing is not very ergonomic at all. But it's workable. Again, like I would imagine that you can probably alleviate a bit of this pain using macros or something like that. But maybe for the next time. Anyhow, so now that we're done with this kind of groundwork and we have the basic scene and the race and whatnot, next video is going to be more interesting with more actual ray tracing and rendering going on. But for now, thanks for watching. I hope it was interesting. See you next time. Peace.